Hello all, welcome to my channel. In this video, we will be talking about how to visualize an AC signal. First, we will see how charges move in a conductor. Then we will see the charge movement for different sample waveforms. And finally, we will see the importance of visualizing. So let's get started. Visualizing is all about understanding how charges move in a conductor. In my previous video, I had explained how to visualize a DC signal. If you have not seen that video, I would recommend you to see that video first. The video will be displayed on the top right of the screen here. When I say charge, for a metallic conductor, it is nothing but electrons. Whenever a signal of any form is applied, these charge carriers move in a certain fashion in response to those signals. Let's take an analogy to understand how charges move in an AC signal. Assume that there are two walls here. And there is a road connecting the two walls. And you are this person. What is your initial velocity here? 0 km/h. And now I give you a challenge that you should run and touch the other wall and come back to your original position as fast as possible. So what do? You, who is at rest now, will start moving in this direction to touch the wall, and once you touch the wall, you'll come back. That's an high level visualization of what you would do when you're asked to run between two walls. But let's go in a little deep and see how your velocity varies between those two walls. So since you want to reach the wall as soon as possible, assume some random point near the wall, close to the wall. Here you would run increasing your speed until this point, after which you will have to reduce your speed so that you can halt, touch the wall, and again come back in the reverse direction. So to summarize, in the forward direction, if you consider this direction to be forward, what you would do is you would the person, that is you, who is stagnant, you will increase your speed, try to move as fast as possible until some point, and after that you will decrease your speed and finally come to an halt, touch the wall. Now when you want to go back to your original position, you would do the same thing but in the opposite direction. So what you would do is, if this is the wall and this is another wall, this time after touching the wall, you will start moving in this direction with an increasing speed, and finally at some point you'll start decreasing your speed so that you can come to an halt here. If you understand this analogy properly, then you can visualize any kind of AC signal, because that is what charges do in an AC signal: move back and forth between 2 points. So if you have a conductor and this is the electron here at this position, assume there is an imaginary wall here and an imaginary wall here. What the electrons would do is, they would move back and forth between these 2 points for any given AC signal. And how do they do it? They are at halt at this position, they will increase the speed, they will again decrease the speed, come to an halt, they will start moving in the reverse direction, increase their speed and decrease their speed to again come to an halt. That is all a electron does for any type of AC signal. This is a more general way of visualizing how the electrons move in the conductor. So let's try to take an sample waveform and see how it moves. We will take a simple waveform. Assume you have a triangular waveform like this, and assume it's a current waveform where y-axis is current and x-axis is time. As I explained in my previous video, current is directly proportional to the drift velocity of the electrons. So you can assume this waveform as velocity of the electrons versus time. So if you have a conductor and you have an electron here, let's assume this time to be t1, this to be t2, this to be t3 and this to be t4. This completes one full cycle, and the same thing will repeat again and again infinitely. So understanding one cycle is good enough to visualize an AC signal. So until time t1, from 0 to here, velocity which was at 0 will increase and reach some point v. So the electron here which was at rest initially, for time t1 it will start moving in the forward direction, and when it reaches this point it will be at a maximum velocity v. From 0 it would have increased its velocity to v by the time it reached this point. If you see the waveform carefully, this distance is equal to this distance. So what it means is the distance traveled by the electrons in time 0 to t1 is same as the distance traveled by the electrons in time t1 and t2. But what is the change here? Electrons which were at velocity v will now start decreasing their velocity and still move in the same direction until they reach this point where the final velocity will become 0. If you visualize carefully, the electron will increase its speed until it reaches this point and then finally decrease its speed by the time it reaches this point. And now the electron which is here has to go back to its original position, which is here. And how does it do that? It does the same exact thing that it did when it came for the positive half cycle. So what it will do is it will start increasing its velocity from 0 and till halfway it will increase its velocity to v. After that it will again start decreasing its velocity to 0 and finally reach its original position. That completes the full cycle of an electron in an AC signal. So let's see how the graph shows this. As you can see, from 0 to t1 the velocity increases, from t1 to t2 the velocity decreases. But the point to note here is that the electrons are still moving in the forward direction. They have not changed their direction yet. But if you take this direction as positive, then the electrons moving in the opposite direction will have negative velocity. Therefore, that is depicted by the waveform here, which maps to the negative velocity on the y-axis. Now for this waveform from t2 to t3, the electrons will move in the opposite direction and again increase the velocity to a maximum value v, and again they start decreasing their velocity and come to the original position where the final velocity will become 0 again. So if you carefully observe in an AC signal, the waveform below the x-axis determines how the electrons move in the opposite direction, and the waveform above the x-axis shows how the electrons move in the forward direction. And in this case, since both of them are same, electrons move similarly in both the directions. Now let's take a different example where the waveforms are not same, so that you'll understand the example better. Assume this is the given AC signal, and this thing keeps on repeating infinitely, and this is velocity versus time. Let's see how the electrons move now. This is the conductor, this is the electron here, and as previously we can take this as T1, this is T2, this point is T3, this point is T4. Right away you can notice that this distance T1 is not same as the distance between T1 and T2. Therefore, electrons from 0 to T1 will increase their velocity and reach some point x. After that point, they'll again decrease their velocity and come to an halt. If you remember the previous example, the point where the electron starts to decrease its velocity is exactly at the midpoint in the path that the electron takes. But in this case, it is not so. The electrons will take more time to increase its velocity to a maximum point v, therefore it covers some more distance, and later in the short period of time it will quickly decrease its velocity to 0 and cover a smaller distance. While going back in this direction, the electrons will increase their velocity from 0 to a maximum value v and cover some distance from here to here and rapidly decrease their velocity and come to an halt. So let me summarize the difference between a perfectly triangular waveform and then a skewed waveform like this. In both the cases, electrons move back and forth, but in the conductor, for the first waveform, the electrons starts to increase its speed and reaches a maximum at the midpoint, and again starts to decrease its speed and come to an halt, and do the same thing in the reverse direction. But for this signal here, that is not the case. The electrons move a larger distance in this direction until it reaches maximum velocity, and rapidly it will decrease its speed to 0, and it does the same thing in the opposite direction, that it will take long time to increase its speed and comes to a maximum velocity and finally comes to 0. I hope you are able to see the difference in how charges move for different waveforms now. I'll take one last example, and probably this is the most common and widely used signal for any AC analysis. It's a sine wave. If you see carefully, it is very similar to the triangular waveform, because in the triangular waveform the velocity starts to decrease at the midpoint, and even in the sine wave the velocity starts to decrease in the midpoint. Therefore, when you apply a sine wave to a conductor, the electrons will increase their speed until the midpoint, they'll decrease their speed from the midpoint and come to an halt, and they'll do the same thing in the reverse direction. Then what is the difference from here to here? If you look carefully, the way the electron increases its speed until it comes here is different in both the case. In the triangular case, the electrons will increase their speed with time. This is velocity versus time, as you know, linearly. But In the sine wave, the velocity of the electrons will increase quickly in the initial part of the time, and it will increase velocity slowly in the next part of the time. And that's the key difference between a sine wave and a triangular wave. In both the case, the electrons will still go back and forth, and the electrons will start to decrease its speed exactly at the midpoint. So why is it important to visualize all this, right? And if you want to answer the questions like why the impedance of a capacitor uh, changes with frequency, or why the impedance of an inductor changes with frequency of the AC signal applied, you need to understand how charges move in a conductor. Once you know that, you will be able to intuitively answer such questions without even knowing any background on the topic. So that's it for this video. In my next video, I'll be explaining why the impedance of capacitors and inductors vary with frequency of AC signals. Till then, stay tuned and thank you.